I'd like to welcome everyone to our first seminar at the Google Bayesian Speaker Series. And we're very, very excited to have Andreas Krause to kick off this series. So Andreas is a professor of computer science at ETH Zurich, and he leads the Learning and Adaptive System Group. He also serves as the academic co-director of the Swiss Data Science Center and the chair of the ETH AI Center, and also the co-founder of the ETH spin-off Latticeflow. So his research has received a lot of awards, including the ACM SIG-TDD Test of Time Award of 2019 and the ICML Test of Time Award of 2020. And personally, I also found Andreas' research having a lot of influence on my own work. In fact, when I was still a grad student, the first paper I read in the Bayesian optimization field was his GPUCB paper, well titled, I think it was Gaussian process optimization in the Bender setting. And every time I went back to that paper, I still found myself getting new insights. So without further ado, I'll leave the stage to Andreas.
Thanks so much for the kind introduction. Thanks a lot for inviting me to this workshop. It really looks like a great program. And thank you all very much for coming. Today, I'd like to tell you a bit about some work we've been doing on efficient exploration in Bayesian optimization and related settings. And of course, this is joint work with a fantastic set of PhD students, postdocs, and senior collaborators who I'll acknowledge as we go along. So this picture here was taken pre-pandemic, and I very much hope we'll be able to refresh it sometime in the near future. So a central question that motivates a lot of the research that we do in the group are questions related to optimized information gathering. So how can we equip learning agents with the ability to actively acquire most useful information at minimum cost? And this is a problem that arises in a lot of different domains. In science, for example, we might want to equip labs with the ability to partially automate experiments, right? Plan, conduct, and carry out experiments based on observations they've made in the past, with exciting applications in drug discovery, material science, and other domains. In robotics, for example, we might want to plan informative paths for sensors to roam around, monitor water quality in lakes, for example, or, for example, learn online to solve complex tasks. And of course, systematic experimentation requires and applies in a lot of other fields like automatic machine learning, of course, recommender systems, and many other tasks. So one running example that I want to use and that we'll see several times throughout this talk is a collaboration that we have with the Paul Scherrer Institute. That's a large federal research center in Switzerland, where we collaborate with to tune their Swiss fell-free electron laser that you can see on this picture here. So that's a 700-meter long linear accelerator, which generates X-ray pulses of extremely short duration. So femtosecond duration, 1/1,000,000th of a billionth of a second. And so with this instrument, you can image extremely fast processes like molecules turning into each other in the context of chemical reactions, for example. And that, of course, has important applications in drug design, material science, and other domains. It's also quite a complicated machine with many parameters that need to be tuned, right? So there's literally moving parts like magnets that shape the beam properties that need to be configured in order to optimize the pulse energy. Now, the laser's property depend also very subtly on environmental conditions like temperature, humidity, for example, and also need to be adapted continuously to application-specific requirements. So it's not just one set of hyperparameters you tune once and off you go, but you actually need to resolve these tasks very often and in a continuous manner. Okay, now this and many other problems like many of the ones that we've discussed in the first slide revolve around the central challenge, namely this exploration-exploitation dilemma. You need to plan experiments in order to learn about some unknown function, some unknown process, and use what we learned in order to make effective decisions. So for example, we need to learn how the laser reacts under different environmental conditions, and use what we learned in order to tune it efficiently online. Now, in many of these domains, the number of choices we have is much bigger than the number of trials we can ever carry out, and the experiments are typically noisy and expensive, right? That means we need to be really careful with what we do. Now, not all is lost, because typically there is some notion of regularity that we can exploit, in the sense that similar alternatives lead to similar performance, and oftentimes we also face a repeated sequence of similar tasks, ideas we'll explore later. And the key question is how we can make use of this regularity effectively. And of course, one natural way of encoding prior assumptions about regularity is the Bayesian viewpoint, and that's exactly what's done in Bayesian optimization. Now, given that this is the Bayesian optimization workshop, I probably don't have to say too much about the problem setting. I'll still do a quick recap to just bring everyone on the same page, also given that this is this first talk in this sequence. So Bayesian optimization concerns itself with optimizing some unknown function that's typically just viewed as a black box, that we can put in some input xt and get out some output yt, which is this unknown function f of xt evaluated up to some noise, which in this talk we typically assume to be zero mean sub-Gaussian. Okay, and so typically we assume we don't have any further information, so we can't get gradients, for example, directly, and typically carrying out those experiments, evaluating this function is quite expensive. And so now the key idea in Bayesian optimization, of course, is to endow this unknown function with a stochastic model, so with the prior distribution of our functions, whose uncertainty we can then use in order to not only make predictions about the function in places where we haven't seen, but also quantify the uncertainty in that prediction. And then we can make use of that uncertainty in order to navigate this exploration-exploitation dilemma, which is typically done by optimizing an acquisition function, which basically tells us how much we gain by carrying out an experiment, either in learning about the function or in terms of finding better solutions. And there's a whole range of acquisition functions that have been explored, analyzed, and applied quite successfully so in the literature. And of course, the key question is really, on one hand side, how should we go about designing those experiments in order to typically locate the optimum of the function as quickly as possible? But of course, another important question that we'll also get to in this talk is, where does this prior really come from? Now, before we talk about algorithms, I just want to mention some of the most important performance metrics that we can think about analyzing these algorithms. So one that's quite widely used to assess performance of Bayesian optimization algorithms is the cumulative regrets, also extensively used in bandits and reinforcement learning, where we just sum the opportunity cost of not knowing the underlying function, right? So we sum over all time steps t of the difference between the optimal function value minus what we got at that time t. Now, in some applications, you might not care about the cumulative performance, but you just might want to find one single good solution, in which case, if you have deterministic function evaluations, the simple regret is sort of a suitable performance notion. If you have noisy observations, typically, if you observe a function value that leads to a good measurement, that doesn't mean that actually the function itself had a high value. So it's usually more useful to look at what's called the inference regret, where you basically look at the recommendation made by the probabilistic model given past data. And these are often quite tightly tied together, certainly bounds on the cumulative regret, for example, imply bounds on the other notions of regret as well. And we'll see several of them used in the context of different applications. In this Swissfell application, since this is really a task where we need to online tune this machine, the cumulative regret is actually a useful notion, for example. So here is sort of a crucially important picture highlighting how the uncertainty is really essential in navigating this exploration-exploitation dilemma, right? So suppose we've carried out a bunch of experiments shown by those pluses here, and now got a posterior prediction, maybe with the mode and most likely function, the posterior mean, shown by this black line, and some uncertainty about the unknown function. And suppose these confidence bounds are well calibrated in the sense that they cover the true unknown function, which is shown in the blue dashed line here. Then as long as these confidence bounds are well calibrated, we can apply the following rationale, right? So if you look at the best lower bound that maximizes this lower confidence bound, then as long as these confidence bounds are well calibrated, the maximum of the function must be somewhere above this green dashed line. That means we can focus exploration really on this green subset of the domain, the set of plausible maximizers, where the upper confidence bound exceeds the best lower bound. And this idea justifies one widely used criterion, this GPUCB objective function, the optimism in the face of uncertainty principle, which of course is widely used in bandits and reinforcement learning as well. But this idea of using plausible maximizers actually is much richer, and we'll explore this going forward. Now, one point I just want to quickly make is that a lot of what we're going to talk about really relies on the fact that we have well-calibrated confidence intervals with respect to the underlying function. Now, at this point, I should point out that here we'll primarily talk about Gaussian process models, which are very widely used in Bayesian optimization. Later on, I'll tell you about some results on Bayesian neural networks and other types of Bayesian priors. Okay, so now if we really believe that we have a prior distribution that describes perfectly the unknown function, right, we believe that sort of nature is drawn from our prior distribution, then of course we can easily enumerate credible intervals, say at some given point x, by just taking our posterior mean plus multiple times our standard deviation. But of course, nature might not really care about our prior, right, might misalign with our prior distribution. And moreover, we not want this the validity of this confidence bound to not only hold at one point, but everywhere in the domain. But fortunately, it's actually possible to recalibrate these confidence bounds in order to really be valid across all points in the domain, as well as all iterations of the algorithm, as well as account for possible model mismatch by rescaling these confidence bounds in a way that depends on the complexity of the unknown function, measured with respect to the reproducing kernel Hilbert space norm associated with the covariance function that we use in this Gaussian process prior, together with some capacity term, which essentially quantifies the effective degrees of freedom of this prior distribution. Okay, and so under those sort of conditions here, basically, where you can calibrate these confidence intervals, you typically can guarantee, for example, bounds on the cumulative regrets after the sorting algorithm. Also, I would like to point out that there's been quite a bit of work since this initial results. For example, one can even, to some extent, handle adversarial corruptions. So go even beyond basically stochastic noise to some limited amount of adversarial corruptions, of adversarial shocks and unknown functions. Now, one first line of work that I want to talk about is work on safety of exploration. And let's go back to our Swissfeld free electron laser. So here, we can't just carry out arbitrary experiments. So in particular, if you're not careful, there can be a radiation damage which might cause some of the magnets in this machine to become damaged and would need to be replaced. And so that we really want to avoid. Okay, now fortunately, there's beam loss monitors that are deployed inside this machine, which can monitor how close we get to violating any of these safety constraints. Okay, and so now that means that we effectively no longer have an unconstrained optimization problem where we want to optimize some noisy reward, but we also have a function that essentially serves as a constraint, which is basically the reading of these beam loss monitors. And of course, now we would like to maximize the function subject to basically not exceeding critical thresholds. Now, the key issue is that both the objective and the constraint in this and many other related applications is actually unknown ahead of time, right? And while it turns out that in principle we can run simulations, so simulate the physics of this machine, these simulations are actually extremely expensive, extremely slow. It's also very hard to really simulate the effect of environmental conditions like temperature and humidity and so on carefully. That means that we actually need to do this optimization and this exploration live on the machine by closing the loop. Okay, so that means that we really want to optimize basically the unknown function under these constraints and need to, of course, ensure safety every single step along the way. Okay, so we basically face a constraint optimization problem with an unknown objective, unknown constraints, and need to ensure feasibility of all our iterates. Now, it should be pretty clear that in general, this is a completely opposed problem, right? So we need to make some sort of assumptions, right? And that's, of course, where Bayesian optimization can come in, right? Where we not only endow the objective, but also the constraint with a probabilistic model. Of course, we can apply sort of a similar rationale that we used in order to reason about sort of plausibly optimal actions to also reason about safety, right? So again, if the unknown constraint function in this case here is covered by these confidence bounds, and we have our safety threshold here, then as long as we constrain exploration to this red subset of the domain here, where this where basically our pessimistic estimate of the function value, right? So basically our lower confidence bound exceeds the safety threshold, then our evaluations hopefully are safe, right? So as long as we get these well-calibrated confidence intervals, we can sort of constrain and cautiously explore. Okay, and so the first algorithm that sort of realized this idea is called SafeOpt, published in ICML a little while ago. And so here we basically endow both the objective and the constraints with Gaussian process priors, and maintain both the set of basically this conservative inner approximation of our safe region, as well as the set of plausible maximizers that I showed before, right? And now one natural strategy that might come to mind is to just use standard acquisition functions like, for example, GPU-CB on this set that we can conservatively certify to be safe. Now, the trouble with this is that this way we wouldn't really explore enough, right? So the optimistic estimate of a function constrained within this red region would be somewhere in here. So we have no incentive to actually explore the boundary, right? And go to sort of regions of the parameter space where that we previously don't consider to be safe. So instead, we also look at the set of plausible expanders that you can see here that are shown in purple, and that are basically sets of points that plausibly allow us to infer additional actions as safe. Now, among all those relevant points, so plausibly optimal or expansive, we basically pick the one that provides as much information as possible, and eventually really figure out that better function values can be found in this region of the space that initially we didn't consider to be safe. Okay, and then the similar sort of regularity assumptions that I've described to you before that essentially assert the validity of the confidence bounds, we can guarantee both safety and completeness of this resulting algorithm. So you can guarantee with arbitrarily high a priori probability, 1 minus delta, that the algorithm will not violate any of the constraints along the way. And we can also basically establish effectively bounds on the inference regret. So essentially bound the sample complexity we need in order to return an epsilon optimal reachable point. Now, the original algorithm had some issues. In particular, this tends to explore the boundary too much, right? So in order to really figure out how far the algorithm can go, a lot of the observations happen near the boundary of this domain. And now, fortunately, there's ways of improving this. And so what we proposed a little while back at NeurIPS is a variant of this algorithm, which essentially does this expansion in a more goal-oriented fashion. So the idea is now you use a standard acquisition function like, for example, GPU-CB or max value entropy search, or another acquisition function that you might like to propose an experiment. If you can certify it to be safe, you carry it out. But if you can't do that, then you effectively plan a path, right? You plan a sequence of experiments that would aim to expand the feasible region towards containing this point that you would want to carry out. Now, there's one more challenge that really arises before one can apply this algorithm to complex applications like this Fell electron laser, namely scaling to higher dimensions. And one of the big issues is that the algorithm, as described so far, really maintains an explicit classification in the domain into points that are plausibly optimal, plausible expanders, and so on. And of course, that is very hard to do in high dimensions. But there's a very natural way of scaling the algorithm to more complex high-dimensional domains by essentially iteratively running it on low-dimensional subspaces. So that's an idea that we explored in the paper at ICML a little while back, where we basically start with our initial feasible iterate that is shown here. And now what we would do is we would propose a low-dimensional subspace, in the extreme case, just a line, and then essentially apply safe optimization on this one-dimensional subspace. Then we would, again, propose another subspace, apply the algorithm in that subspace, and sort of keep going. And of course, there's different ways of how to do that, how one can, for example, propose these low-dimensional subspaces. So in the paper, we analyze local convergence, even just for randomly proposed subspaces. But turns out one can also make use of the Bayesian model in order to propose subspaces in a more informative manner. So for example, if you use a Gaussian process model, this automatically implies a distribution over its gradients at any given point, and one can make use of this prior information in order to propose a direction that is likely to increase the function value. So in this way, combine ideas from sort of local and global optimization. And now using this algorithm, my students, Johannes and Manja, really went ahead and applied it live on the Swissfeld-free electron laser. And I'd like to show you just a few results on this. So the kind of experiments that they would be carrying out essentially go as follows, right? So they would start with parameter settings that our physicist collaborators had manually found. And then they would detune the machine, right, to a setting that yields much worse performance, and then basically use different algorithms to try to recover and try to find better solutions. And one common technique that's applied a lot in the domain are local search techniques like MELDA-MEET, for example. It's a heuristic. It doesn't have any explicit safety analysis, but still fails rather rarely and also finds decent solutions relatively quickly. But still, because of its local nature, it actually often gets stuck in local optima in comparison with this more global method that I've described to you before, which actually in some cases finds quite significantly better parameter settings, oftentimes better settings than the experts had started with. Now, since then, there's also been a number of other applications of safe Bayesian optimization. In particular, I'd like to point out one exciting one, and that's work by Yanan Sui, who was one of the co-authors of the SafeOpt paper that I mentioned to you before. And it's also an application that actually motivated the research that we've done in this space. And this is on an application of using Bayesian optimization basically for a therapeutic application in spinal cord therapy. So they basically work with spinal cord injured patients who, after an accident, had lost control over their lower limbs, and who have been implanted a little electrode array that you can see here. And then basically Bayesian optimization is used in order to really optimize muscle response and treatment signals. And of course, this is a super safety critical application. So it's absolutely important to really cautiously explore in the context of these clinical trials. So another topic that I'd like to talk about is exploring another limitation of optimistic exploration. And the motivation, yeah.
And just sorry to interrupt.
Sure.
I saw Riff raised hand.
Once again.
Anyone?
Oh yeah, are we taking questions as we go, or are we holding them till the end?
I'm fine to take maybe one or two questions now, if you like.
Yeah. Can you go back a couple slides to the FEL?
Yeah.
So one more forward. No, the graph.
The
result graph.
Yeah.
So do you feel like the experts have any guess as to like what a truly optimal solution to this would look like? Like how much do we think we're in a slightly better local optimum versus do we really think we're getting close to the global with this method, or how do you think about that?
Yeah, that is a very good question. It's hard to assess. I believe they have a fairly good understanding of how the machine works, right? And I think they believe they find good solutions, but of course it's hard to really prove that not much better solutions can be found in this context. I think the bigger issue is really they can find pretty good solutions by essentially manually operating the machine. The problem is that really what is the best solution changes quite dramatically as the system goes through these different fluctuations. And again, they need to be adapted to these application requirements. So that's where the issues really arise.
And one more question quickly. For this particular experiment, like what's the time scale? Like how long did it take to do the 750 experiments?
So the measurements, they are really quite fast and actually aggregate already over multiple measurements. So I think here essentially experiments are in sort of the tens or hundreds of milliseconds or so. So it's relatively fast.
Got it. And of course, the graph here of the method, I mean, it goes higher quite early. So if you're even more constrained and the experiments are more expensive, it's an even better approach. So
yeah, arguably, yeah.
Great, thank you.
Any other question?
I also have a question that I asked in the Q&A.
Okay.
So
whatever you like,
yeah, I was wondering, like for SafeOpt, there's a problem of how well the probability is estimated, right? And if I actually used similar things for an application in robotics before, and we're sort of treating it as a level set estimation problem. But then the problem, the problem was actually, I mean, the issue was quite similar in the sense that we were trying to keep it in the safe region, but but the probability estimated was from a prior given by ourselves.
Yeah. So absolutely, I'll get back to this a little bit, right? So a key question, of course, is where does this prior come from, right? And I want to tell you about some work exploring this question later on. So maybe if you don't mind, we can get back to the question in the Q&A afterwards.
Yeah, sounds good. Thanks.
Okay, sounds good. Okay, so I want to explore another limitation of sort of optimistic exploration, complementary to sort of safety. And that's the following, right? So if you think about essentially optimistic exploration, then it's basically a form of uncertainty bonus, which is something that's very commonly used in bandits or reinforcement learning, right? So essentially, you would trade your posterior mean, say, with the uncertainty you have about the function. And this uncertainty essentially quantifies the lack of information about the function at this point. Okay, now the trouble is that just because you're uncertain about the outcome of an experiment doesn't mean you're going to learn anything from it, right? So think about starting off with a fair coin, right? Flipping it a bunch of times. If you already know it's fair, right? You still are completely unsure about what's the outcome of the coin flip. So you're not going to learn anything from that experiment. Okay, and so in practice, one effect where this manifests is essentially heteroscedasticity. And that's really an effect that you can see, for example, on the SysFL application, so that the amount of noise quite substantially varies according to the experiment that you can carry out. Okay, so the noise is no longer constant, but actually depends on the input and varies with it. Fortunately, it varies with it with a relatively smooth or regular manner. And that basically gives hope of being able to exploit essentially the heteroscedasticity in this model. Okay, now, why is this a problem with, say, optimistic exploration? And for that matter, actually, a lot of other acquisition functions that are used in Bayesian optimization. So the reason is the following. So let's look at a super simple cartoon example. Suppose there's two sort of operating modes, A and B, and two possible detectors that we can apply. Detector 1 is very precise, has low noise. Detector 2 is very noisy. Okay, so now, of course, the performance of the machine only depends on the first switch, right? Whether we're in mode A or B, not which detector we're using. Okay, so it means we still have 4 options, right? Which mode to use, which detector to use. But of course, the performance is the same for option A1 and A2 versus B1 and B2. Now, of course, if you obtain noisy measurements, right, we get much more noisy observations by using the high noise detector versus the low noise detector. Now, what would, say, optimistic exploration do? Well, so we would construct confidence estimates on these unknown parameters here, basically. But these confidence estimates, they might make use of the fact whether we have lower noise or not, but they would still essentially yield the same uncertainty about this unknown parameter, irrespective of whether the measurement is low or high noise. Okay, so it means that while uncertainty, basically optimistic exploration here would recommend to pick either B1 or B2, it couldn't tell us which of them to prefer. Okay, so it really fails to distinguish epistemic uncertainty due to the lack of data from aleatoric uncertainty that's just depending on the amount of noise in the experiment. Okay, and so now, of course, one natural strategy to improve here is to directly reason about the informativeness of a measurement. Of course, similar ideas have been explored in the context of Bayesian optimization, for example, in the context of maximum entropy search or max value entropy search, and so on. Now, I want to talk about one criterion here that's actually been originally proposed in a beautiful paper by Daniel Russo and Ben van Rooij a few years back in the Bayesian setting. And they propose basically a different acquisition function, which essentially trades in terms of a ratio, a bound on the instantaneous regret. So that's sort of the suboptimality of action X divided by some amount of information that we would get by that experiment X. Okay, so essentially by minimizing this ratio, you prefer either to have low instantaneous regret or an informative measurement. Okay, and now it turns out that this framework, which sort of was proposed in a specific Bayesian context, is actually a much, much richer modeling framework. And we've been exploring this in a series of works with my PhD student, Johannes Kirschner. In particular, it's actually quite a flexible framework in terms of reasoning about sort of different information functions that can be used in this context, and also for a whole range of different sequential decision tasks. But one maybe simple way to think about it is you could, for example, just use mutual information of our experiment with respect to the unknown function. And that then, of course, just essentially becomes a function of the signal to noise ratio, right? So the ratio of the epistemic versus the aleatoric variance in our experiment. Okay, so now you might wonder a little bit of where sort of does this ratio come from. So this ratio comes from actually a quite simple analysis. If you think about the cumulative regret as just the sum of the suboptimalities of those experiments, we can just add and multiply the square root of the information function, apply Cauchy-Schwarz, in which case we now get essentially a sum where the first term is this information ratio, so the squared regret divided by the information function, multiplied with basically the sum of the information, essentially values of the experiments that are carried out. And now what we can do is we can upper bound basically this maximal information that we can obtain. And that's sort of a common technique used in analyzing Bayesian optimization now. And so what's we're basically left with is this information ratio here, psi t, as well as the bound on the maximum information that we can obtain. Okay, and now essentially this ratio is exactly what the algorithm tries to minimize. You can, as long as you can minimize this ratio, you can immediately get sort of a regret bound for an algorithm. Okay, and now the key thing that's sort of left to do is to obtaining an upper bound on the instantaneous regret, but that can actually be very naturally extracted from confidence estimates, right? So if you again take this picture that we talked about before, and basically you want to obtain a gap estimate for actions x1 and x2, then we can again just take an optimistic estimate of the maximum of our function, which is this green dashed line here, and just compare it with the pessimistic estimate of the function value for these two different actions, right? And that will give us basically an overestimate of the suboptimality of these two different actions, as long as these confidence bounds are well calibrated. Okay, now basically given these gap estimates, we can very easily run this algorithm. It's just sort of a minor modification of algorithms like UCB or expected improvement and so on. And for basically homoscedastic, this is basically homoscedastic linear bandits. Essentially, there's no difference between optimistic exploration and sort of information-directed exploration. But if we have heteroscedasticity in the noise, then we can actually improve substantially. So the first major improvement we can get is by using better estimators, by making use of the fact that we know that some of these observations are more noisy than the others. So you can just use the likelihood function that's sort of tailored to the task. But a second major improvement we can get by using a better exploration criterion. So the first improvement is basically a better model. The second is a better exploration strategy. Okay, and both really help substantially. And that actually holds much more generally. So in fact, it holds in a very general model of sequential decision making called partial monitoring. So that's been originally proposed a number of years back for sort of finite action spaces, but it can actually be seen as a form of generalization of Bayesian optimization and a whole range of related problems. So abstractly, you basically consider an agent interacting with an environment. So every round it picks an action from some compact set of actions, and nature has some unknown function that, of course, the agent would like to optimize. This function can also depend on some side information. So in this free electron laser example, this context side information could just be, say, the temperature or humidity that we currently measure. And now the agent wants to optimize the reward, which is just the function evaluated on our action context pair. Now, in the standard bandit setting or Bayesian optimization setting, you would assume that we basically get to see a noisy measurement of this instantaneous reward. Right? That's the setting that we've discussed so far. So the power of this partial monitoring framework is that it allows you to also deal with situations where the reward itself is not actually observed. So they can decouple the reward generation from how you obtain information about the unknown function. And in fact, and what we propose in this call paper is basically a framework where we can essentially use general linear observation operators. So these are basically just linear functionals that take essentially this unknown function f and just predict the real vector. So it's basically a much richer measurement model. And one very natural consequence of this is that now by just choosing this feedback operator, this observation operators, sort of in the right way, we can essentially recover a lot of different variants of Bayesian optimization that have been explored in the literature. So for example, Bayesian optimization with derivatives can actually be captured because gradients are just linear functionals, or Bayesian quadrature. So if you, for example, want to carry out functions in order to integrate some unknown function, can be naturally modeled because essentially integration is just a linear functional. Similarly, one can do things like dueling bandits, right? So for example, optimizing a function purely based on comparison of function values, as long as you can get a noisy estimate of the function difference between two actions, you can model this as a linear observation functional. Okay, so this is basically a very rich modeling framework. And what's the nice result is that you can basically essentially use a single algorithm that automatically specializes to essentially all these different settings and guarantee sublinear regret essentially across this whole range of different settings. And so here's just a sort of a little cartoon example of this in the context of this free electron running example that I've described to you before. So two of the decision variables that you optimize over is basically the relative positioning of essentially the sample that you want to image with respect to the beam properties. So you can basically move this little plate here along the x and y axis. So these are two of the decision variables among many others. Okay, and normally what you would want to do is you would basically maximize the integrated intensity on that entire target. Now, instead of just treating this basically as the black box observation, what we can also do is essentially inject sort of a sensor array on front of this sample and obtain essentially a pixel measurement, right? So essentially a much higher resolution measurement of how the beam looks like everywhere on that plane. However, by doing so, of course, we deflect light from the target, and as a consequence, basically don't really illuminate it, right? And hence get not really any reward with respect to this underlying application, right? So, but one can naturally model this now in this partial monitoring framework, and basically, in this case, get substantially improved performance by essentially using this information-directed exploration compared to just naively using optimistic exploration. Okay, and so now this also scales to more complex tasks and environments. So in fact, heteroscedasticity is not only common in Bayesian optimization or bandits, but it's also a very common phenomenon in reinforcement learning. And so in particular, it can arise due to heteroscedastic reward functions, heteroscedastic transition models, basically state aliasing that arises from partial observability, and so on. So there's lots of sources where essentially basically the amount of noise varies according to different state action pairs, for example, when estimating state action value functions, for example. And so what we explored is to essentially take this information-directed sampling criterion, but use it as an exploration strategy in deep reinforcement learning. And so here, we now wouldn't use Gaussian processes, so this typically involves a lot of data. So here we would use maybe Bayesian neural network models, but one can, at least in a heuristic manner, still extract estimates of epistemic and aleatoric uncertainty, for example, from Bayesian neural network ensembles that have been used in the context of distributional reinforcement learning. Okay, and so here are some results on using this to play Atari. So the starting baseline is of course, the celebrated DeepQ network results by DeepMind. Since the original results, there's been some improvements already published in the literature on using distributional reinforcement learning, showing that by careful uncertainty quantification in the Q function, one can actually improve performance quite a bit. So this is basically using now a bootstrapped DQ network. So it would DeepQ network. So it basically just uses a convolutional architecture, but multiple value heads that essentially capture the epistemic uncertainty in the Q function estimates. And all we do is we take this architecture, the same way to train it, and so on, but swap out the exploration criterion. So instead of just doing epsilon greedy, we basically apply information-directed sampling, and it quite substantially improves performance. Similarly, we can take a different architecture. So this is an architecture that not only tries to quantify epistemic uncertainty in this Q function estimate, but also the aleatoric uncertainty by basically really modeling and predicting quantiles, which was also shown to substantially improve performance. And simply by swapping out the exploration criterion basically one can get substantially improved performance. So from here to here, you basically use a richer model, a more faithful model that sort of captures the uncertainty better. And from here to here, it's basically using a more informed exploration strategy. And so the benefit really comes from essentially learning more quickly. Okay, so the last part of the talk is I want to talk about one really essential issue in Bayesian optimization, structured bandits, and also reinforcement learning tasks that use uncertainty like the one I've described to you right now, namely this question of where do we get our priors from, right? And that's a question that was already alluded to in some of the questions earlier. And of course, so far, we have just assumed that we have a prior distribution over this unknown function. And for some applications, like certain robotics applications, for example, it is sometimes possible to come up with sort of a meaningful, semi-well-informed prior, for example, based on some first principle physics knowledge about the underlying system. But generally, in domains we don't really know too much about the underlying system, it's very difficult to sort of manually specify this prior distribution, of course. And so all the reasoning that I told you about before, right, both in terms of performance, about safety, and so on, of course, really crucially relies on having well-calibrated prior distribution. So this is really absolutely a crucial task. And so now, of course, one very natural question is, can we sort of learn the prior itself? Okay, and so one way to sort of think about doing this is to essentially take a collection of related tasks and then essentially treat this problem of learning a prior as sort of a meta-learning problem, right? Where we basically try, starting from the hyperprior, would apply some sort of meta-learning procedure to obtain a hyperposterior distribution, which can then be used as a prior distribution for downstream sequential decision-making tasks like Bayesian optimization, for example. Okay, now, of course, in principle, there's a lot of possibilities of how one could apply meta-learning. So in the work that I want to talk about here, which is a paper that's going to come up at ICML this year, basically, we built on some really beautiful work by Pentina and Lampert, as well as Amit and Meyer, that motivates meta-learning from a perspective of packed Bayesian inference. In particular, to derive an optimization formulation of optimizing over a family of hyperpriors that basically minimizes a packed Bayesian generalization bounds on the transfer error, on essentially the error of transferring predictors across multiple related data sets. Okay, and so now if you do this, then essentially what the base learner does is essentially applying posterior inference on that learned hyperprior distribution. And now this prior work is conceptually really elegant. However, it's very hard to make work in practice, in particular, very hard to scale to large problems. In particular, the key issue is that this prior work relies on a computationally very difficult nested sort of bi-level optimization problem, where one has to essentially, in order to obtain, say, gradients for the outer optimization problem, solve a complex variational inference problem within the inner loop. And that's really hard to scale to larger problems. And so what we found out, and that's what the core of this ICML paper, is that this problem, and sort of a slightly modified optimization problem that's motivated from basically this packed Bayesian point of view, actually yields a natural closed form solution. So basically has some really nice structure, which allows to avoid this nested bi-level optimization and basically results just in a very simple kind of cost function to which one can apply standard techniques from variational inference and approximate probabilistic inference. So we'll not go into much detail of this method, but I'd rather tell you about some results that can be obtained from it. And so we'll start with just some cartoon illustrations. So here we start with a collection of meta training tasks. So these are very simple sort of 1D regression problems, right? Where basically each of these colored sets of points here corresponds to a task, like all these blue points are basically one regression data set. The green points are one regression data set, and so on. And so these are all generated just from basically sine curves with slightly different phases and frequencies. Okay, and so now what we do is we basically just take very few samples from each of these tasks, only about 5 samples from each of them. So it's very, very sparse data. Apply this Bayesian learning method to learn this hyperposterior. And here on the right-hand side, you can see samples from this hyperposterior, right? And you can see that this quite naturally captures, even though it was trained on very little basically training data, very naturally captures sort of this sinusoidal shape of these underlying functions. And now, of course, one can use this downstream, right? And whereas just using uninformed priors can really lead to poor predictions if conditioned on little data. If you essentially use this meta-learned prior distribution, you get much more, arguably much more meaningful, not only more accurate predictions, but also much more meaningful uncertainty estimates in the unknown function. So this is sort of some simple cartoon illustration, but in the paper we also quite extensively discuss results on real experiments. So there's some experiments on this Swissfell free Electron laser that I've described to you before. So here basically each task corresponds to a different tuning session, right? Say optimizing the hyperparameters under a given set of environmental conditions like temperature, humidity, and so on. And this other data set is basically a time series forecasting data set of patients in an intensive care unit. So essentially here, each data set, each task corresponds to a different patient. And data set is essentially a time series of measurements that are obtained in the ICU. And the goal is to essentially forecast predictions in an autoregressive fashion. And so in both of those data sets, we compare against sort of standard non-meta learning techniques like Gaussian process priors or Bayesian neural networks with hyperparameters that are tuned on related tasks, but otherwise no structure is sort of shared across tasks. We compare also against neural processes, right? A technique that's been proposed for meta-learning nonparametric functions, as well as prior work, including what I've referenced before, basically based on packed Bayesian meta-learning, as well as the Bayesian variant of MAML with basically this PACO results that I've described before. So this optimal hyperposterior. And in some cases, you really get quite substantial improvements, both in terms of prediction error, but maybe more importantly, also in terms of calibration. So here are some results, basically. So what you, of course, want for downstream decision tasks is really that your probabilistic model well captures the unknown function in regions where you don't have any measurements, right? So that's essentially you want to get sort of a situation that looks like this, where basically your 95 confidence intervals, say, contain roughly 95% of the test data. So you want to avoid situations that look like this, right, where these confidence intervals are really miscalibrated, where, for example, they might cover only 50% of the test data. And of course, one can quantify this by comparing, say, the empirical quantiles with the predicted quantiles of the model and essentially assess their deviation. And so now also with respect to this calibration, essentially this new meta-learning method really yields state-of-the-art performance against these different baselines. In some cases, here in the Swissfell example, really quite dramatically reducing the calibration error. And so now one very natural question is, of course, can one use this to sort of close the loop and use it in context of Bayesian optimization? And that's something that we've most recently looked into quite actively. And I want to tell you in sort of the last few minutes. And it turns out that one has to be very careful to really get this to work. So if you just use this basic method, it actually doesn't work so well. And the reason for this is that basically this packed Bayesian analysis really has been designed for essentially dealing with IID data, where essentially your training data is really representative with respect to the different tasks. And of course, if you apply any sort of closed loop algorithm like Bayesian optimization or other sequential decision tasks, then you very systematically get non-IID data. Okay, and that can cause problems, as we'll see in just a moment. So let's just start with sort of a vanilla GP here, right? Where you sort of have this nice property that essentially the GP would acknowledge where it's unsure, right? So if you go away from your data, typically the uncertainty goes up quite substantially. Okay, that's sort of a nice intuitive property that, of course, encourages exploration, right? That these Bayesian optimization and related techniques really rely on quite substantially. Now, if we say generate data from a sample collection of tasks like those here, we can basically obtain this Bayesian optimal hyperposterior that I've described to you before. And even though it sort of captures the shape of this function pretty well, it tends to actually be quite confident, maybe too overconfident in regions where it hasn't really seen any data, right? And that is essentially because it's sort of optimized to essentially treat the data as ID samples from this underlying distribution. And so now what we've shown most recently, and it's a paper that'll just be on archive tomorrow, is basically a way of regularizing the predictions of this Bayesian model to essentially behave like a GP if you go away from your data. So it sort of leverages the rich kind of posterior means and covariances that you can meta-learn from related tasks, while at the same time keep capturing sort of this intuitive property of Gaussian process priors to essentially acknowledge uncertainty far away from your data, right? So in these regions here where you previously were overconfident, it now is actually quite unsure. And that has really major effect if you want to use this downstream in a Bayesian optimization task. So here are some results in sort of an AutoML context. That's, of course, a setting where Bayesian optimization is really widely applied now, right? Where you might start with some data set and you want to find hyperparameters for machine learning models by essentially sequentially proposing hyperparameters, training the model on some validation data set, and then closing the loop to propose the next experiment. Okay, now, of course, one natural way of sort of leveraging experience of trained models on related data sets is to essentially treat Bayesian optimization just as the second stage of a procedure where we first would meta-learn a prior distribution, a Gaussian process prior distribution, for example, on essentially the observed validation performance of some hyperparameters on some data sets, and then use those in order to inform the prior that's used downstream. Okay, so that's certainly a technique where sort of sharing of information has been considered quite a bit in the literature. And I'll show you about some comparisons with work that's proposed in the literature. So here's basically some results on this OpenML benchmark. So that's basically a fine-grained evaluation of a bunch of different machine learning models, ranging from generalized linear models to XGBoost and others that have been evaluated on a lot of different hyperparameter settings on 38 different data sets. And we basically play back from this benchmark in order to simulate the training performance here. So this is just a vanilla GP on essentially how it improves across basically the different iterations of the algorithm. So this is random search. So of course, in general, if you don't use an informative prior, you wouldn't really expect Bayesian optimization to do much better than random search in general. So we really need to make use of sort of prior information in order to be able to do better than random search, at least in terms of the simple regret metric. And so here we compare against various techniques that have been proposed that meta-learn basically Gaussian process priors or related sort of non-parametric priors, also neural processes, for example. We also compare against this PACO method that I've described before, which is basically the one that in a way sort of treats the data as IID, so it's not really been designed for this sort of task. And while it initially quickly finds sort of good solutions, it basically gets stuck and doesn't keep improving. And if you apply this functional regularization, you can actually get quite substantially improved performance across basically these tasks. And so here's the corresponding results on the inference regret, which essentially just looks a little bit more noisy, but basically tells the same story. And the last set of experiments now to go beyond sort of this two-stage setting to really an iterative setting, where we essentially start with the data set, run Bayesian optimization to sort of find good hyperparameters, and then basically add this to a data set of measured validation performance, use this to refine the hyperposterior and consider a new data set, and sort of go on, right? And so essentially in this iterative setting, really the decisions taken by tuning the algorithm on past data essentially becomes the very data that the hyperposterior basically is being trained on, right? So essentially, basically need, in order to do well here, you need to solve this exploration-exploitation dilemma on the meta level. Okay, and so in these results here, basically we plot the inference regret, so effectively sort of the best solution found after carrying out about 20 experiments on each of these different data sets. So here each vertical bar basically corresponds to a new data set that we transit to on, again, these 3 different machine learning models. And here's just the vanilla GP that doesn't share any information across the different tasks. And here's different baselines like learned GPs, rank-weighted GPs. This is a method that essentially meta-learns a mean and covariance in a Bayesian linear regression model, and so on. And here's essentially this functionally regularized meta-learned prior that yields really very robust performance, outperforming these other methods across these different data sets. So that's basically what I wanted to discuss. So I think in order to really realize the potential of Bayesian optimization and related tasks on challenging real-world applications like those discussed here, and of course, many other exciting ones out there, I think there's really fundamental challenges that really need to be addressed related to safety and efficiency, but also to many other challenges like scaling to really high-dimensional domains, complex action spaces, partial observability, state dependence, and many other questions. So super exciting open questions to be working on. And I'd like to conclude by just thanking all the collaborators in this research. Here's a few references if you want to read up more on some of the work I've presented, and I'd be very happy to take any questions.
Cool. Thank you so much, Andreas. I know that the time is probably up, but we'll leave the room open. And for anyone who wanted to ask questions or in the discussion, feel free to stay. Anyone have questions?
I would be really delighted to hear a little bit more detail on kind of, what you think the most important limitations or open problems of the work you presented is. I think that would be, really, really exciting for me to hear. Oh, by the way, great talk. I really enjoyed the talk. Very excellent. Thank you.
Okay, thanks a lot. So I think there's certainly a lot of challenges here. So it depends on sort of different facets of this work that I've presented, right? So in terms of this information-directed exploration, there certainly are, okay, I mean, I think, okay, let's put it like this. So I think there is, on the theoretical side, certainly major challenges on essentially lifting some of the theory that we now understand somewhat well for Gaussian processes to other models like Bayesian neural networks, for example, right? So that I think is one big question mark, right? And of course, if it really comes to questions like safety and so on, really being able to assess when can we trust these models and when we can't, I think is really one of the fundamental challenges, both from a theoretical level, but also, of course, from an empirical level. That said, right, I think also in terms of the more practical algorithms that I've described, there are still substantial open challenges like those I briefly mentioned at the end of the talk, like, for example, really dealing with high-dimensional complex action spaces, for example, mixed discrete continuous, complicated constraints under sort of what makes feasible inputs and so on, handling state dependence, right, pushing some of these ideas beyond, say, Bayesian optimization and bandits to, say, reinforcement learning tasks and so on. I'm not sure if that answers your question. I'm happy to go into more details with any.
No, that was really helpful. Great. Thank you so much.
Sure. Any other questions?
So I have a question regarding the evaluation criteria that you mentioned at the beginning about cumulative regret, simple regret, and so in multi-arm bandit, we know that there is a difference in terms of the rate between pure exploration and cumulative regret exploration. In GP, as far as I know, this difference between the rate doesn't exist. So basically, in terms of the rate, theoretically, if we solve the problem with cumulative regret, we can use it for pure. But we know in practice, this is not the case. So what is the status or state of the art in terms of pure exploration? If I don't care about the loss during training and only my final answer should be accurate, can you elaborate a little bit, and what is the state of the art there?
Yeah, it's a great question. I don't think it's still really fully resolved yet. So I haven't seen any fine-grained analysis of the simple regret and how they really substantially improve on the rates you can establish using cumulative regret. Even though in practice that sometimes can really be achieved. I think that's definitely a very interesting, generally open direction.
Okay, thank you.
Other questions?
So I'm curious about the results earlier on the learned GP. What exactly is learned GP?
Yeah, so the learned GP is basically just a GP with automatic relevance determination. So it has some more hyperparameters, but no fancy covariance function also. Yeah.
So it's learning on the current task, or?
So no, it's learning across tasks. So it basically reuses information from past tasks in order to essentially improve on the parameter estimates. So essentially, it sort of across tasks learns which dimensions are more important than others. That's effectively the effect that you get in these experiments.
I see. So it's like sequential getting data from each task and gradually refine it? Or?
Yes. So these are two settings that I talked about. So in this second setting, right, it's really so essentially you solve one Bayesian optimization problem on one data set, right? This way you sort of collect how well some models work on some data sets, right? And now this way, sort of you build a large collection of evaluations, essentially, which we can use then to refine the prior, basically, right? And so this is the context in which I've talked about and evaluated, for example, this learned GP model here, right? So essentially, then going through this loop here, it would always make use of essentially how well past models worked on past data sets, for example. It would use this in order to refine essentially the hyperparameter estimates. So that's a very simple baseline.
So I have a question. So
yeah.
does in this iterative Bayesian optimization, does the model ever forget about the previous runs?
No. So here basically, okay, so what happens is as follows, right? So all the past observations are essentially incorporated into the hyperposterior, right? So essentially all the past tasks, they're used in order to refine basically the prior distribution, right? That's then used downstream, right? So in that sense, it never forgets in a way. Of course, it may forget technically through the inference procedure, right? But conceptually, that's essentially how it maintains past experience.
So in that case, you don't need to like save the data somewhere in order to revisit it every time to train it again?
Yeah, so I mean, in this case, so basically, so you still have to solve this optimization problem, right? To essentially minimize this packed Bayesian generalization bound, right? This criterion, I mean, like the one discussed in the paper. And that, of course, makes use of all the past observations, right? So that's essentially a cost function, right? Where you basically use the replay buffer, right, of all the past observations you've seen, right? All the models you've evaluated, essentially on all the data sets.
Got it. Thanks.
Mm-hmm.
Andreas, great talk.
Hi, Daniel.
I got a question for you. So,
sure. Yep.
So for the packed Bayesian stuff here,
yeah,
we thought about a like a non-stochastic version. Like, is there some notion of like meta regret?
Yeah, very interesting question. Something to look into. So this is basically really here. So the theory also that we elaborate on in the SciSmL paper, this is really based on IID samples. So IID across tasks. Happy to talk more offline if you like.
Sure.
That's a natural question when you're thinking about it. So.
All right.
Any other questions? Yeah.
I hadn't heard about the IDS acquisition function before. It was very interesting work. Was there a statement on that IDS is strictly better than using UCB, for example?
Okay, so we've done now IDS is really sort of a framework of algorithms, a collection of algorithms, because it's parameterized basically through one side the gap estimates, so they are standard essentially in the approach, but particularly parameterized through the information function. And now it turns out through specializing it with different information functions, you can somewhat get different algorithms. So what I've described to you so the result in this call paper from last year is basically for this general family of essentially linear and kernelized partial monitoring problems. So that's really a quite rich family of decision problems. There's essentially one choice of information function such that the algorithm essentially performs optimally, at least in sort of a worst case regret sense. So it turns out you can classify these partial monitoring games according to sort of how difficult they are. So bandits turn out to be simple games. They turn out to be, there's also harder games like dueling bandits, for example, are strictly harder. You get worse rates in terms of regret. That's the sort of beautiful work also for finite partial monitoring games prior to our work that really essentially paints quite a complete picture on the difficulty of these decision tasks. And so what's really nice about this IDS result, what we established in this call paper, is that there's essentially one algorithm that's sort of essentially, at least in a worst case sense, optimal across these different settings. And it's practical. You can run it, and it actually does quite well across different domains. There's also some really nice work by Johannes Kirschner, as a PhD student in the group, and his collaborators looking at essentially algorithms for linear bandits. And by carefully designing an information function, they were actually able to show that with IDS, you can get sort of a first algorithm for linear bandits that is basically optimal both in kind of the worst case regret sense, but also satisfies instant dependence bounds. So essentially, you can also sort of use nice instances. So it's essentially simultaneously asymptotically optimal, makes use of sort of instance-specific properties. So if you face a nice instance, you can benefit, and it's optimal in sort of the worst case sense. So it's really quite a rich modeling paradigm.
Right. So, but if I understood correctly, in the example you showed,
yeah,
you used kind of a pessimistic estimate for for this information, which is kind of like a confident, like a upper bound or lower bound situation.
Yeah. So basically, what we use the pessimistic estimate for is for the gap estimate, right? So if you go, so here's basically. Okay, so this is what I wanted. Okay, so this is basically so the algorithm minimizes this ratio, right? So you have the gap divided by the amount of information you get, right? So sort of try to have a small gap. At the same time, you try to gain much information, and that's basically what you optimize. Okay, and now so now what you're pessimistic about is this gap estimate here, right? So that picture essentially shows how to construct that gap estimate, right? By comparing sort of the optimistic estimate of the optimum minus the worst case estimate for the actions you play. Right? That gives you the estimate. For the information function, this is basically what I showed here is basically a form of mutual information.
Okay, and for the information function, you have to form an estimate for these the noise, the actual measurement noise and the actual physical noise.
Yeah, exactly, right. So this is where it shows up, right?
So here the application specific.
Yes. So the simplest form information function, right, is literally just the Shannon mutual information between the experiment y of x and the unknown function, right? And if you work out what it is, it's basically just this log signal to noise ratio, right? So essentially, look at the log of 1 plus essentially the ratio between the epistemic uncertainty divided by the aleatoric uncertainty. And so also for this partial monitoring result, all that changes is now the likelihood function, right? So essentially, instead of just looking at essentially a Gaussian likelihood, so basically a Gaussian likelihood for a pointwise observation, you look at the Gaussian likelihood of a general linear measurement, right? But if you start with the GP and you still sort of observe linear functions, everything just remains nicely Gaussian.
Right. Okay. So I can always apply this. Where I have a GP, like Bayesian optimization problem with a GP model, I can always apply this.
Yeah, you can apply this quite generally, absolutely. So, and then so also you can sort of tailor these information functions to do a bit better. So here's essentially an information function that's sort of inspired by max value entropy search. So I want to highlight this really nice work by Zian or Goffis once more, where basically what you can do is you can basically quantify the mutual information between your measurement and the function value at the optimistic optimal action. So it's basically not at the optimal action, but at the action that might be plausibly optimal, basically. And that sort of captures a similar sort of effect, but it's very efficient to compute, right? It's all just Gaussian initial information and so on. So there's no approximations needed. And that's essentially the results that I showed in the plots here, right? Where this basically behaves sort of like UCB in the homoscedastic case, but substantially does better in the heteroscedastic case.
Okay, so could I say that the answer to my first question is yes, it's always as good or better?
Yeah, so I think you can always make it work at least as good as.
Okay.
So let's put it like this, right? But essentially, in most cases where we've seen it, it essentially does as well as UCB or better.
Okay, thank you.
So yeah, thanks for the talk.
Mm-hmm.
And for I assume like more complicated models like meta learning priors work. There are lots of hyperparameters of the model itself. So how did you go about choosing them? And are there any advice you have for practitioners who want to apply your work?
Sure. Well, you'll just sort of do meta learning on top, right? And just step up one level in the Bayesian hierarchy. No. So yes, of course, that in the end, you'll never be able to avoid some form of hyperparameter tuning. So those experiments that I showed, we really tried to keep it as clean, as straightforward as possible. We described, of course, the exact experimental protocol in the paper. I think it's important to really have the right kind of experimental framework, right? To really, so of course, for sequential decision-making tasks, evaluation is always harder, right? So it's not just sort of a simple train test split as you might do, say, for supervised learning, but especially, for example, for these iterative Bayesian optimization tasks and so on, right? So typically you can, for example, leave out some tasks that you train the method on, and then take some separate tasks for evaluating the methods, right? That's effectively what we report here. Okay. Any other questions?
I have a question, but it's
Sure.
It's a bit kind of a naive question, perhaps. Hello from Google Zurich, by the way. Yeah, so I'm really interested in the idea of this meta learning, the prior, and I'm trying to think about how it relates to transfer learning, which is kind of like a point estimate of something similar, but it's not the same because you use a different objective. So I'm just trying to understand.
Very similar. It's very similar, right? So it's sort of hard to really draw a boundary, right? It's a form of transfer learning. Yeah.
Sure. But you were trying to minimize the transfer loss between the prior tasks. So,
yeah, in some sense. So transfer learning also, I mean, it's not always consistently defined and so on, right? So what's often looked at in transfer learning is the transductive setting, where you already know there's a set of tasks, right? And you basically want to learn a model specific with respect to a certain target task, right? You might think about covariate, I mean, basically sort of adapting to the corresponding covariate shift and so on, right? And so here, what you generally want to do in meta learning is maybe more inductive. So in some sense, you want to essentially summarize all the past tasks into one, say, hyperposterior model that you can then apply to a new task. But of course, that's one approach that you could apply to a transductive transfer learning setup. You might just not be able to do as well as you could by making use of that information.
But then also when you're doing when you're training the posterior using this learnt prior, I guess you're minimizing something which is the sum of two loss functions, the loss on the sort of prior tasks and the loss on the new task, which is different, I guess. Because in the transfer, that's all forgotten as soon as possible.
Yeah, so here, yes, so exactly. So here, we don't do this any further, right? So essentially, once we have the training tasks, right, we learn this hyperposterior based on them, and then we just use that as fixed downstream, right, for the next, say, Bayesian optimization task, for example. Right?
Okay.
So
I'm not sure I understand that point, but I'll read the paper and it'll be clear.
Okay.
Thank you very much.
But actually, effectively, so this prior work on packed Bayesian meta learning that I mentioned, for example, by Pentina and Lampert, and Amit and Meyer. So that essentially is maybe in a way closer to sort of multitask learning. So they really have to maintain essentially a posterior approximation for these different tasks and refine this online.
Okay.
So that's sort of where this nested optimization comes from.
How does that scale to deep nets?
Yeah, that's the problem, right? It's very difficult to scale. So, and that's so I mean that's what we essentially resolve in this ICML paper.
Cool.
Yeah, I guess we can wrap up. And if anyone have questions, I mean, did you mind if we share your email, Andreas?
That's fine.
Yeah.
I think it can be found anyways online. So
that's probably available online too.
Yeah, very happy to follow up otherwise. Yeah.
All right, thank you so much. It's really
thanks, Andreas, for staying through your dinner time.
Sure. Yeah. Thanks a lot for inviting me. It was fun. Okay. Bye, everyone.
Thank you.
Bye.